Hi, my dear students. I am Dr. V.V. Kamesh, Professor of Mechanical Engineering, Aditya University, Sorampalam. In the present class, I want to introduce the problem of transportation, that means the transportation problem in operations research, or we can call in optimization techniques. Okay. So here, actually, the transportation problem, how it will arise, I will show you on the screen. Now I will share my screen. I think you are able to see it. Okay. So I'm opening the Paint 3D. Yeah. So what is actually the transportation problem? Generally, the word transportation meaning moving from one place to other place, right? So here I will take so I'm putting the heading for something, 1 minute. Need to minimize this screen. Okay. Yeah, I'll take the pen. Right. Yeah. Now I can put my heading. Oh, the thickness is somewhat bigger one. Okay, I will reduce the thickness. Okay. 2 or 3 pixels. Okay. Yeah. Now you can see the heading. This is transportation problem. Right. So what is this transportation means? One place to another place, the goods are being transported. The goods means actually the finished goods. So after manufacturing is completed, then it is being packed and everything is printed on it. Then it is ready to be sold to the customer. So these finished goods, they are having two choices. One is to the godown and second one is direct to the market. Okay. So any finished good will have only these two choices, right? Now in these two choices, market. So here the market means your customers, right? Now you remember one thing, the customers will not be located in a single region, just like a group, right? So the customers will be diversified in different locations, okay? Now, let us suppose that your manufacturing locations also diversified. Manufacturing locations, there are many, okay? Customers locations, there are also many, okay? Suppose the manufacturing locations I am having A, B, C, okay? And let us suppose that D also there, right? And customers locations are 1, 2, 3, okay? Or otherwise I will say C1, C2, C3, okay? Here I will take A, B, E, D, okay? So not to have the C common, I am taking A, B, E, D. 4 manufacturing locations and 3 customer locations I am taking, right? Now I will take another screen and there I will explain. So what is the actual problem of the transportation? Now let us suppose that some manufacturing locations are there. Okay, otherwise I will take M1, M2, M3, M4, right? So these are all manufacturing locations. So same product is being manufactured anywhere. Let us suppose that M1 is Chennai, M2 is Bangalore, M3 is Bombay, and M4 is our Surampalam, right? So in 4 locations, the same product is being manufactured. Same product with the same quality, everything is the same, right? Now, the customer locations I'm having C1, C2, and C3, right? Now I'm having the transportation problem preliminary is, now look here, the C1 customer center is having a demand 200 units, okay? So they are giving me a purchase order 200 units, and C2 is giving a purchase order units 100. C3 is giving the purchase order for 500 units. Now, I don't want to make anything inventory in my godown. So whatever the purchase order, the same amount I want to produce. So 200 plus 100, 300 plus 500, it is 800, right? Suppose M1 capacity is 150 units, M2 capacity is again 150 units, okay? Now the M3 capacity is, this is 250 units, and M4 capacity is 250 units, right? So 150, 150, 300 plus 250, 250, so 800. So whatever that is my demand from this C1, C2, C3, same number of units I am producing 150, 150, 250, 250, right? Right? So total demand and total supply both are equal, right? Now you remember what is the actual problem? The problem is mainly, now I am writing to the right extreme, that is cost. What is this cost? Cost of transportation. Because the one thing, whatever you are making the same product, it is being manufactured, the cost of production is the same, but what about the cost of transportation? It will be different from one place to other place, because the transportation cost is directly dependent on the distance. Got it? So as you travel more distance, more petrol or more diesel will be consumed, and you need to incur more amount of cost. Okay. Now the problem is how to make your profit to be equitable or optimum. It is depending on the reduction of the cost of transportation between M1, M2, M3, M4 and C1, C2, C3, right? Suppose I'm having M1 to C3, the cost of transportation per unit is 5 rupees. M1 to C2, it is 4 rupees. M1 to C3, it is 3 rupees. M2 to C1, it may be 7 rupees. M2 to C2, 6 rupees. M2 to C3, 5 rupees. Like this, M3 to C1, M3 to C2, M3 to C3, M4 to C1, M4 to C2, M4 to C3. Like this, I'm having a matrix of the values between M1, M2, M3, M4 and C1, C2, C3. Okay. So these are called sources. All these are called destinations, right? These are called sources and these are called destinations, right? Now I will take very small thing. I will show you in the Excel. Okay. So I'm taking a new blank workbook. So this is sources S1, S2, S3, S4. Okay, sources are destinations. Okay. So on vertical, I'm taking sources. And here I'm taking the destination D1, D2, D3. Okay, got it? So, okay, all this is forming a table. Now, the cell value, now you are looking the yellow. This yellow is referring to the cost of transportation between the station S1 to the destination D1, right? So the cost may be 5 rupees. Okay. Let us take a very small thing. Now S1 to D2. Again, I'm taking this one, this may be 6 rupees. S1 to D3, it may be 4 rupees, right? Okay, S2 to D1. Now I'm taking with another color. Take another one. So this may be 12 rupees, 8 rupees, and 9 rupees. Now S3 to D1, D2, D3, I'm taking with some other color. So this is 11 rupees, 5 rupees, and 3 rupees. Now S4 to D1, D2, D3, I'm taking with some other one, 20 rupees, and 16 rupees, and 14 rupees, right? Now, the S1 is having a capacity 150 units. So here I am having capacity. So I am showing the capacity with some other color. Let us suppose I am taking this color. So capacity 150 units, next 250 units and 250 units, right? I am taking the middle, right? What is the total? It is 800. Now the D1 is having a demand, right? So demand I am taking with the same color. So, right. So this demand is 100 units. For this it is 200 units. For this it will be 300 plus 500. Okay. Now the total demand and total capacity. Now look here. 150 plus 150 plus 250 plus 250. I got 800. Now 100 plus 200 plus 500, 800. So both are equal, right? Now the total demand of the destination warehouses or godowns and the capacity from the sources or factories or production stations or manufacturing locations, both are equal. Now the problem is, look at the source S1, 150 units, right? So these 150 units is to be transported to which destination and how many units? So to the D1, how many units I need to disperse? I don't know. For D2, how many units out of this 150 I need to disperse? Again, I don't know. For D3, how many units from your 150 is to be transported to D3, right? So these numbers are the cost parameters. Now, how many units I need to allocate for this? Actually, the cost of transportation will be 5 rupees for D1, 6 rupees for D2, and 4 rupees for D3. So how many units I need to transport? It is directly affecting my cost of transportation, right? Suppose I want to minimize the cost of transportation. Out of the total matrix, the cost of transportation between S3 to D3 will be 3 rupees only. So 250 units I can transport to D3. What about the remaining? If I take only the least cost alternative, some of the units maybe with the S4 to D1, it is 20 rupees per unit. So no single unit can be transported from S4 to D1. So it is illogical. So optimization cannot be done here. So for optimum transportation cost, so we need to have multiple solutions, right? So there are so many combinations will be available because S1 to D1, I can transport 1 unit, 0 unit, 0, 1, 2, 3, up to 150. So I'm having 150 combinations, right? Same thing for S4 to D1, I'm having 250 combinations. S4 to D2 also 250 combinations. So like this, If I take the how many combinations are possible, manually I cannot calculate. So there may be supercomputers that only can calculate, and we are calculating the optimum transportation cost. But manually, if we want to identify the least cost combination or optimum cost or optimal solution of this transportation problem, so what is the problem? I think you are able to understand well. So what is the problem means? How many units to be allocated from S1 to D1? Question mark. How many units from S1 to D2? Question mark. Right? So these 5, 6, 4, 12, 8, 9, 11, 5, 3, 20, 16, 14, all these are per unit cost of transportation. So how many units? Suppose 5 rupees is S1 to D1. Suppose I am transporting 10 units, right? So I am transporting 10 units from S1 to D1. That implies what is the cost of transportation? It will become 10 into 5. So it will be 50 rupees. Okay, I will write here rupees 50. So like this, if I transport some 20 units from S1 to D2, so 20 into 6, like this, 50 plus 80 plus 20 plus 120, like this, the cost of transportation will be added from each and every source to the destination. All the cells will be allocated from 0 to some value, right? So finally, I will get total cost of transportation. Okay. Now, this total cost of transportation is to be optimized. That means optimizer means I need to get the least. Okay. Got it. So the problem of transportation means you need to minimize the total cost of transportation by optimum allocation of the resources, right? Now I am taking this problem as an explanation for you, or otherwise I will take um, another also I can take. Okay, I will do one thing. So whatever the problem I gave as an example or in the important material, so I will take that one. Just 1 second. What is it? Okay. So in this, so don't by heart this solution because the solution is from the ChatGPT. So you follow in the lecture whatever I'm saying. You follow this procedure. Okay. So this is the find the initial basic feasible solution using northwest corner rule, right? So what is this northwest corner rule? What is initial basic feasible solution? I will explain one by one. This snipping tool I'm taking and I'm cutting this. Right. So this I will take to the Paint 3D. Okay. No. Selecting. So I will select a new one. Okay. Okay, right. Now I'm taking to some extent. Right. Now what to do? Now what is this initial basic feasible solution? You look here. Suppose I'm having this space. Okay. This space generally we are calling the feasible region or solution space. Okay. I told you in the first unit, there will be some feasible region. Okay. In this feasible region, suppose there is an optimal solution at this point. So this one is optimal solution, right? but directly I can't reach the optimal solution. So somewhere from the outer side, maybe I'm entering the solution space from this side, or this side, or this side, or from this side, like this, right? Just like to enter into India, I can enter from Kashmir, I can enter from Tamil Nadu, I can enter from Bengal, I can enter from Gujarat or Punjab, right? So the optimal solution is your capital. Okay, just as a small comparison. So reaching the optimal solution from different sources, right? What are those different sources? There are minimum. So entering into the space. So entering into feasible region, that solution is called initial basic feasible solution. So entering into the feasible region, the solution becomes initial basic feasible solution. So suppose I'm having some point in between, right? Region, but this is not optimum. This is not optimum, right? So it is far from the optimum solution. Suppose I'm having some other solution, I'm taking this red point, so there is some gap. Okay. Now I'm taking this purple at the border, near to the border, very far from the optimal solution, right? Now, you think once, how many initial basic feasible solutions can be possible in this infinite solutions, right? Now, there is some problem here. Out of these infinite problems or infinite solutions, that means initial, okay. Out of these infinite solutions, I will take one of the solution, okay. I will take one solution, okay. I will check it whether it is optimum or not. Optimum or not, okay. If it is optimum, I will declare, okay, the solution is reached. This is the solution, hence approved, okay. If not, then what I will do? I will follow some methodology, right? There is some methodology. So there is some algorithm from your language. So there is some algorithm to reach the optimum. So by this, I will reach the optimum. Now, for your first mid examination, up to this, finding the initial basic feasible solution only in the syllabus, right? Is it clear? Now we will learn how to get your initial basic feasible solution. Now you may ask one doubt, sir, already the initial basic feasible solutions are infinite solutions. Why we are taking the different methods? Just by means of the mathematics, we can check so many solutions. And they found some methods, they are very close to the optimum, or they are having a very good route path in these algorithms towards the optimum, right? So reaching our capital, so you can start from to reach India, you are having some salient points, important points. So there are actually, so reaching India from Rameswaram or some other Kanyakumari village or from village in the West Bengal village in the Gujarat, that is different. Reaching from Chennai to the Delhi, reaching from Bombay to Delhi, reaching from Bangalore to Delhi, this is different, right? Just there are some important basic feasible solutions to reach the optimum. Feasible solutions. There are some methods available to us. So there are nearly 5 methods are available, right? First one is north-west corner rule. Okay. Second one is least cost method. Third one will be Vogel's approximation method. Okay. And there are some more two methods are there. These are actually nobody is using, right? But you are also automatically the last one will be column minimum method. These two methods are least compared when compared to the least cost method. So these two are deleted from the general use. So we are using mainly northwest corner rule, least cost method, and you one by one how to do it. Okay. So the methods are very easy, easy to understand. Okay. Okay. Now I'm erasing this. I will explain you how to do one by one, one by one. In your examination, you can make it very clear, starting from initial basic feasible solution by northwest corner rule, right? Now I'm drawing this table once again. Look here. So the first row, first column. So this will be for S1. This will be for S2. This will be for S3. So this is the D1. I'm taking a bigger table so that the values get minor. D4 and the last one column is supply, right? Now, for your understanding, I'm taking with the different colors, 7, 9, 18, and this one. Demand for the stations are 5, 8, 7, and 14. Okay, 16 plus 8, this will be 34 I got. So 5 plus 8, 13 plus 7, 20 plus 34. Okay, 20 plus 14, 34, right. When these two are equal, then only we can start the transportation problem. They must be equal, right? If they are not equal, that is, I'm taking this 19. Okay, I will take with some dark color, right? Okay, so I'm taking this 19, 30, 50, 10, 60, 20, and this 40. You can write in any manner, don't worry. No order, just I'm filling the table, right? Now, I copied all the cost parameters to the left of this particular cell. Now, if you look at a particular cell, right? Look at a particular cell, right? Cost in the left side, okay? Now, how to make the allocation? What is the rule? North, west, corner rule. Northwest corner means top left corner. Okay. So now these allocations I'm putting with some line like this. So this cell I'm writing a small subcell. I'm drawing like this. Okay. So top, this is northwest corner. So northwest corner is to what's the priority? S1 D1 is the highest priority. Now D1 is having the demand 5 units. S1 can give 7 units. So you are asking units to D1, right? Then you cannot supply to S2, you cannot supply to S3. So the capacity of this or the demand for your station D1 is completed, right? So I'm writing somewhere S1 D1 5 units, right? Now from my study appeared, okay? Now from the 7, already 5 is supplied to you, supplied to D1. So S1 station can supply another 2 units only, right? Now look at this updated table. In this updated table, now what is the top left? In this table, the top left will be requirement and what is your capacity. Capacity is 2. You are asking, so the capacity of S1 is over. The capacity of the requirement for D2 is completed. Only 2 units, still 6 is pending. Right? Now, which is completed? S1 capacity is completed. So, in the next table, I am removing this S2. In the next table, I am removing S2. Okay? Right? Now, this is my updated table. In this updated table, now you tell me again, what is the northwest corner? Look at this. S2. Now look at this. S2, D2. Now tell me what is the capacity and what is the requirement. Your requirement is 6. Your capacity is 9. Okay. So 6 is changed. Completed. Now your supply becomes still 3 is there. Now here my allocation S2, D2, I am having 6 units. So D2 is over. So my D2 requirement is over. Now I'm having the updated table is S2, S3, D3, D4. Now what is the top left? S2, D3. So here I'm multiplying 3. The maximum ichimano. So this is 3. The demand still it is 4. Okay. Now what is the units? Now what is completed? For each and allocation, you remember either one supply will be completed or one demand will be completed. So here S2 is completed. Now you look at the table. There is one special rule. If you are having the last row or the last row, you need not apply any rule. Directly fill as it is. Now look at this table. What is the 18? Here supply is 18. So simply write 4 here, 14 here. Okay. Understood. So this S3, I am having 4 units and S3, I am having 14 units. Right. Clear? Right. Now in this way, are being allocated for all these destinations. So S1 to D1, D2, D3, D4, how many? Everybody, every unit is being allocated to its destination. So the basic feasible solution, right? So because the time is running by the Zoom, I will continue in the next video. Thank you.